Without further ado, let's get started. So, zero knowledge is a technique or set of techniques that are becoming more used in the last decade or so for doing what can be thought of as verifiable computation, and in some cases, private computation. So, the core intuition for zero knowledge is that if we have some function f, we have f of x, and we want to claim that f of x equals y, where either x is private or the function is expensive. Expensive in the fact that it's like a very large function. Say it takes a megabyte or a gigabyte of data to express f. The core intuition for zero knowledge is that we get to hide part of the left-hand side of this equation here, so that it is either succinct to send information about the potentially large function to y or to the verifier, or that we get to maintain the privacy of x, or both. So I tend to think of this as like the core intuition behind zero knowledge is that we're going to hide either x because it's sensitive, or f because it's fat. And that's kind of the reason that we'd like to use zero knowledge, is that we would like at the end of the day the verifier to be able to say, yeah, I believe that. I can verify that the thing that you just said is true without having to receive a large commitment to, or a large function description, or a private piece of information. So onto zero knowledge. There are a couple of fairly sort of trivial examples of why zero knowledge, or how zero knowledge, and we're going to go over two of them and then get to two sort of more low-level examples and try to get you up to why sort of ZK circuits, or why ZK circuits work, or how they work is sort of the target goal of this lecture. So we start here. What does ZK mean? And as far as it goes, ZK is really just these three things. You have completeness, soundness, and zero knowledge. And that's if a system has completeness and soundness, it's an argument system. And I can give you as a reference a book by Justin Thaler on sort of more about argument systems. But the addition to an argument system that makes a zero knowledge proof, where before you would have effectively a proof without this sort of zero knowledge component. With the component that is zero knowledge, we have a zero knowledge argument system. And to sort of expand on what each of those things mean, we have a prover who wants to produce some proof to send to the verifier, which is often spelled pi. We want to prove that the prover knows x and has computed f on x, such that f of x equals y. And that's before, if f is fat to express, or x is private, we want to send, instead of the whole statement, we want to send some shorter, simpler thing to check, pi, as opposed to something long and hairy to express. And so we have three properties that we particularly care about. One is completeness. Completeness and soundness should make intuitive sense, in that if I want to prove that something is true, and I'm willing to loosen my definition of what a proof is, where if we were to think about a mathematical proof, we might expect something to be proven by induction, or proven by contradiction. We're proving by a probabilistic statement that would be hard to break out of. So completeness says that an honest prover, that is a prover that follows the algorithm and actually computes the function, they always get to a valid thing that the verifier believes. So that's a fairly sort of straightforward way of thinking, that if you follow the algorithm, nothing bad happens. No one blows up. And the second thing is soundness. So what if we do have a dishonest prover? We want to sort of know whether the dishonest prover is, how powerful the dishonest prover is going to be. Well, we want the second property, that soundness. The dishonest prover is going to fail almost always. With very low probability would a dishonest prover be able to succeed. And there's some controversy about the soundness, for instance, of the Starkware prover, where the Starkware prover has somewhere in the order of 28 bits of soundness, which is a very low bit number. But because that is a not permissionless role within the Starkware ecosystem, as far as I understand, there are only trusted positions that can act as that prover. And those trusted positions have to also, on top of that fairly low bit security, compute a proof of work challenge. So for each attempt at violating that prover role, the Starkware prover would also have to compute an expensive sort of proof of work challenge to go along with that. So, but in a nutshell, soundness is this property that if we have a dishonest prover, they're very likely to fail. And so maybe we could get around this by saying that we're going to only trust people that we know to be the prover, and then maybe we could have lower bit security, and then use some cryptographic sort of extra computation to sort of sound that up. But the standard assumption is that we're talking about dishonest provers, or if someone is able to be a dishonest prover, then we want to make it impossible for them to obtain a correct-looking proof for some statement. And then last, we get to the final sort of eponymous property, zero knowledge. And the heuristic is that zero knowledge is that the verifier gets 0 bits of information about the secret X, or more precisely, the way we often prove zero knowledge in sort of the context of a theoretical proof is we have this premise of a simulator. And so the simulator concept, I think, sort of misses a lot of people on the first pass. The whole premise of the simulator is that if we were to, say, see the output of a zero knowledge proof, could we simulate plausible inputs going back up the sort of chain of reasoning without knowing anything about the actual inputs, the true inputs? And so the intuition here is that if we can simulate a entirely valid looking transcript going all the way back that looks plausible, then we've effectively shown that if we can simulate this transcript without any extra knowledge, then the sort of conclusion there is that the transcript reveals nothing, such that even a sort of no knowledge third party could say, I could make that up. But the first party couldn't have possibly made it up because they're not working for respect to the start. They're working sort of from something that they need to convincingly say to the verifier, well, I'm going to prove this. So that might not have made super much sense. And there's a really good example coming up. So let's start with our first example. So our first two examples are going to be kind of trivial. We have this sort of opportunity to sort of drill down on completeness, soundness, and zero knowledge in a very easy sort of like zero knowledge proof context that we can kind of deliver to anyone, maybe your mom or whoever, is like the example of where's Waldo. So if the prover here has seen Waldo and wants to prove where Waldo is, well, they could just take a large sheet and cut a hole in the middle of it, the Waldo hole, and say, hold the sheet over the book and say to verifier, okay, so look, I found Waldo because I can show you where Waldo is behind the little hole here. And so verifier is convinced, yeah, okay, that seems legit. There's obviously Waldo there. And so the question is, does this proof have our 3 properties, to sort of get some intuition for how each of these work? And so for completeness, what was the actual protocol that the prover was supposed to run? Well, first they were supposed to find Waldo. If the prover actually found Waldo, they should always be able to put the hole over Waldo to say, here's Waldo. And the verifier will believe it because Waldo will actually be there. And the second property is soundness. So the next question should be, okay, so if this guy is evil and wants to cheat the verifier, what can evil prover accomplish? Well, they're going to have to put a hole somewhere. And if they randomly pick a location, say that there are, for the sake of convenience, 100 different locations that the prover could have chosen to put the hole, then they're only going to succeed with 1 out of 100 probability. So with reasonably low probability, will the evil cheating prover succeed? So the protocol is nominally sound. And the last question is it zero knowledge? And so the zero knowledge part of this proof would be that if the verifier gets more information than they should have from the proof, other than, for instance, the prover knows where Waldo is, then the protocol is not zero knowledge. And maybe there's like a little bit of background stuff going on behind Waldo. Like maybe we have like this little snippet of a guy right here. So maybe the verifier gets a little bit more information than we might expect from an actual zero knowledge proof. But that information is going to be reasonably small. So effectively it is basically zero knowledge. Now, to be pedantic about this, or to be formal about this, what we would actually want to do to say, how do we show a simulator where the entire protocol of messages can be simulated by some verifier who's trying to simulate stuff? Well, the way that would work is that our simulator is trying to, maybe we should use a different color not to be overlapping with soundness. So our simulator is going to try to say spoof using the final message, spoof using our final message, the rest of the transcript. And so in this proof, the transcript is really just one message. So the prover says that we're going to say, give some coordinate. So message 1 is some x and y coordinate. So there's actually nothing for the simulator to simulate here. So this is why this is kind of an awkward example for a zero knowledge proof context, because our simulator couldn't actually, it doesn't simulate any other messages in our transcript. And usually when we're doing something like this, we have a multi-round sort of interactive protocol, and we'll get to that next. And so the next sort of like easy example is color blindness. And so we now have a sort of different example where our prover is going to send several messages, and there's going to be an interactive challenge and response period in this proof for Bob, who sees color, who claims to see color, to convince Alice, who says, no, I don't believe that you see color, that he sees color. And so we're going to go through the same exercise and maybe flesh out the premise of the simulator with a little bit more detail. So Bob has 2 circles, one with green and red spots, the other with just red spots. So if Bob says that these 2 pictures are different, Alice, since she is colorblind in this example, says they're the same picture. So Alice is going to take the balls behind her back and switch them, or maybe not. So Alice is going to say repeatedly, take the balls behind her back and put them back in front and say, did I switch the 2 balls? And if Alice can't tell the difference between these balls, but Bob can, Bob will always be able to say, yes, you switched them, or no, you did not switch them. So if we do this a bunch of times, Alice might say, on the first time, well, you had a 50% chance to get that right. On the second time, you had another 50% chance to get that right. So if you got them both right, then you had a 1 out of 4 chance. If we do that 80 times, we have 80 bits of security that Bob was actually correct. And both of these examples, maybe you've already seen, but they're fairly good to work through as an example to sort of understand these properties of completeness, soundness, and ZK. So if Bob actually can see color, that is, if Bob can actually run the protocol, then Bob will be able to distinguish between the red ball and the red ball with green flecks in it. So is it complete? Yes, it is complete. Second, if Bob is lying, that Bob cannot actually see cannot see the difference between red and green. If Bob is colorblind as well, then Bob will not actually be able to fool Alice, except with 1 out of 80, 1 out of 2 to the 80 probability. So that case also holds that soundness, we get this 50% increase in probability that Bob is being honest every time we run the protocol. And finally, we have our zero knowledge issue. So Alice didn't learn anything about what's going on with green, what green looks like, who can see green, except for Bob can see green. So the only thing that Alice learns in this example is that we get the existence of green and that Bob can tell. And Bob might be lying. There might be something else about these balls that Bob can tell apart. Maybe, in fact, there is a secret string that hangs off of one ball. And in fact, Bob can't tell the difference between these two balls, and Alice doesn't notice the string. But what Bob has proven is that he can tell the difference between the two balls. So Alice gets to know that Bob is telling the truth, that there is a difference between the two balls, and Bob claims that that one is red and one is green, or one has green flecks in it. Now we want to express this. We want to find a way to express this in our sort of simulator language. And the way that we sort of might do that is that we do actually now have a transcript of messages. So on round I, Bob is going to respond to Alice, where Alice says, let's say bi b1 minus I, with I in 0, 1. And Bob says, if Bob can distinguish between b0 and b1, then Bob says true or false, that Alice switched them. So if we have some history in our transcript where we have Alice's message that says b0, b1, and Bob says true, and we say b1, b0, and Bob says true, and so on. The question is, can we look at the history of the transcript and say the simulator can effectively make up the scenario in which the balls were arranged? Well, the simulator actually gets the full transcript of what's going on, so of course the simulator knows kind of, well, the balls got switched. So they can sort of like make post-rationalization of sort of what happened in the multi-round protocol. The simulator kind of gets to know everything, but they didn't know anything to start with. The simulator might not be able to, or is not able to distinguish between the balls, but can act like they did just based on the transcript. So there's sort of the intuition there, is the simulator can basically say, take up the transcript and say like, yes, this all makes sense, and sort of be like a cat staring at the newspaper. So that's the zero knowledge component, formally speaking, in this protocol. And so now we're going to switch to a more mathematical example, and this is actually something that is relatively useful. And so we're now going to switch to Schnorr's sigma protocol for proof of knowledge of exponent. So for the next step in our ZK evolution, we're going to try to have Bob convince Alice. We're going to try to have Bob convince Alice that he knows some X. And so this could be useful for a variety of reasons. And sort of as an aside, we might have, for instance, a signature scheme, which is exactly what this is. So if Bob knows X, then Bob would certainly be able to create a valid signature with that private key, and that would prove that he knows X. So you could say this scheme that we're about to do is sort of a variation on a signature scheme. So how are we going to do this? Because we don't actually care about any external message, which would make this a real signature scheme. We just care that Bob knows X. So how shall we construct our signature scheme? Well, one thing that we could do is that we could say that Bob is going to commit to some randomness. We're sort of like skipping over sort of some of the motivation here. But a lot of the time, if we want to prove that something is true, as usual, there's like a reasonably useful example or a reasonably useful opportunity to say, anytime we want to prove something is true, let's take some randomness and try to fold it into the structure of the problem somehow. And so Bob is going to commit to some randomness. He's going to say that I will commit to some random value that is not x, and then you should be able to challenge me, and I will try to fold x into that value. And so Alice is going to do exactly that. She's going to challenge Bob with the value a. And something that you might remember is that the structure of a Schnorr signature is actually quite similar to this. In fact, the final message in a Schnorr signature is almost exactly ax plus r. So we're now challenged with this way for Bob to prove that he has some knowledge of the exponent x, and that he's committed to g of the r, and that Alice has challenged him with a. And finally, Bob says, okay, so I'm going to hand you back ax plus r. Now, the question here is first, well, let's go down our list here. And let's check that this is actually correct in the first place. So Alice needs to check that this message is correct, and the way she is going to do that is that obviously Bob couldn't compute ax plus r without the knowledge of x. Otherwise, he broke the discrete log and obtained x from underneath g to the x. So Alice says, so if I say take the public key, capital X, to the value of a times r, this is just equal to g to the x to the power of a times j to the x to the power of r. And s is the same for z, as we've calculated up here, or let this z be the final message that Bob sends. Alice can check for herself that Bob has correctly followed the protocol and probably has knowledge of x. In fact, almost certainly has knowledge of x, because he otherwise would have just guessed luckily and had a collision in this sort of exponentiation. So completeness-wise, if Bob does actually know x, then he can obviously compute ax plus r, and Bob will win every time. There is no chance that that Alice is like, no, you don't know x. So completeness-wise, Bob is perfectly well off in this example. And soundness-wise, the next question is, what would the probability that a cheating Bob confuses Alice? And so that probability would be that if instead of x, we say we had cheating Bob who said that we're going to do x prime. In that case, we need the probability that the ax, g to the ax prime plus r is equal to g to the ax plus r. And since we can sort of look at this as a random value from the field, we could sort of say weakly that the probability that these two values collide is pretty low. And in fact, if g is a generator, it is zero that these two values collide. So you might intuitively believe that there is a pretty strong soundness argument here. We have completeness and we have soundness. Now the last question in our protocol is, can we say that Alice learns nothing about the value of x based on this protocol? And obviously Alice would learn nothing about the value of x from Bob's initial commitment. So the question is, what can Alice peel off of ax plus r? And this is the same analysis that we do for Schnorr signatures, in fact. Now, Alice does not know r. She does know a. So she can maybe say, well, let's compute a inverse and say, take this times, and we're going to do Alice in red here, times a inverse. Well, then we could say that Alice computed x plus a inverse r. So now x is standing by itself, but it's still shielded by this nonce. So the question is, like, have we won anything? if we take the addition of x plus some other random value, because this is effectively a random value, did we learn anything about x? And of course, if Alice learns r, then she can say just compute the inverse of this term and add it in and obtain x by itself. So our nonce is of course important to this analysis, that Alice can't obtain r or else she obtains the secret key, which would be a big bad. But Alice doesn't have access to r. And I can give you basically that's the decent sort of intuitive direction. But if we wanted to be more rigorous about this, we need to prove that Alice can't have access to r based on this g to the r term. That she can't break this, and that she can't break this based on two values that she knows nothing about. So the formal analysis would be a statement that if Alice could obtain x, then she could either obtain the discrete log of g to the r, or the discrete log of g to the x, or she could break or she could determine some statistical deviation from a random value plus another random value. That is, she could say distinguish these two values from pure randomness. And since x and r are supposed to be chosen at pure random, that should not be the case. So that is the sort of formal way that we would go through this and try to provide some security analysis. So out of that, we got that Alice should not have gotten any information about x. And more precisely, we can now do a sort of better example of what a simulator would look like. So taking our transcript here, let's see if we can find some space. I have left insufficient amounts of space, so we're going to move our guys here. I'm going to go over here. And now the simulator is given the message transcript g to the r, the challenge a, and the final response is z equals a plus r. So here's an example of our simulator. Let's say that our simulator has z, and our simulator is going to say, okay, so we're going to make up some value for x based on r and a. So our simulator is going to say, okay, so what can I do here? We're going to make up that, say this value was 2. The simulator can make up, the simulator can make up a value for r, and no one will be the wiser. So our simulator is arbitrarily going to say that let r equal 2. Then say a was equal to 3. Then we're going to say, try to work backwards and come up with a valid value for x that would convince anyone else. So the only thing our simulator is bound to is that they need to obey that the z looks correct at the end. So maybe we had that z, for our example, is, shall we say, 11. So we're going to work backwards to solve x. And we're going to say that our simulator has decided that r is equal to 2, so z minus, or 11 minus 11 equals ax plus r, but we said that r was equal to 2, so we're going to say 9 is equal to 3 times x, so we're going to say that x is equal to 3, and we're allowed to make up basically this message. We don't have to stick to the transcript that we were given, we just need to stick to the value that we received at the end and come up with a plausible transcript preceding it. So then we're going to say that we keep a constant, and we then decide that our generator is going to be 7, so let's say that g to the r is just 7 to the 2 is 49. And this can all occur over whatever finite field we want. The point of this exercise was to show that the simulator, given the final message in the protocol, can come up with a reasonable sounding transcript for the rest of the protocol. And that is the sort of way that we prove zero knowledge, is that the simulator can take that transcript and sort of come up with something in reverse order. And that, in fact, like the sort of intuition here is that the order really matters. Going backwards, you can do anything you want, but going forward, the prover should be entirely bound to a value. So this is the Schnorr's proof of knowledge of exponent, also known as a sigma protocol. And I'm not actually sure why it's called a sigma protocol. But the premise here is that sigma protocols are generally 3-round protocols where there's a whole class of them where the prover says, I'm going to commit to some randomness, and the verifier is going to respond with something. And then the prover finally responds with the final message in the protocol. Now, before we move on to the next section, that's been sort of a quick whirlwind tour. This is our first actual sort of like use case of a zero knowledge proof. So our first two examples were sort of like useful ground setting. This is the first case where we have like an actually relatively useful protocol. So I want to stop and ask if there are any questions about the first 3 examples given. Killer. All right. Then moving right along, we're now going to take that proof of knowledge of exponent and do something slightly more interesting with it. So what we want now is we want to do something that's directly building on the previous example. We want to add or prove that we know the addition of 2 values. So the prover in this case is going to say, I know now x, but also y, such that x plus y is z. And we're going to wander into an example here. And we will not get to how do we do the same thing with multiplication. And what did I do? All right. So did I delete that entire example? I must have deleted the example. Balls. Okay, so notes are not killing it here. All right. Well, we can use the previous protocol to prove that we know x and y, such that x plus y is equal to z. And the way we would do that, and I see a couple questions in the chat, so let's see. So would I missed this the first time. Sorry, 0x0f. So would the verifier Alice be polynomially bound for knowing the proof, assuming that she doesn't know x? Usually we want our verifier to be even better than polynomial. We want them to be sort of logarithmic or constant time in the actual computation that the prover does. So would the verifier Alice be polynomially bound for knowing the proof, assuming she doesn't know x? Maybe the other statement there is that we generally assume that our sort of adversary in most cases is our prover. Because our prover is classically thought to be like Merlin or a supercomputer or a wizard. So the question that I think to sort of shoot for the answer for would be, would the verifier be polynomially bound for knowing the proof, assuming she doesn't know x? Also, she doesn't need to know the proof. The prover hands her the proof, but she would be polynomially bound for trying to obtain x out of the proof. So yes, she is polynomially bound, and all of our actors are generally polynomially bound. And the yeah, maybe that helped clarify. I think I see some typing going on, but I'm going to move on to talking about ZK addition. Right. So if we want to run this previous protocol just for a couple of new values, then we can actually get a proof that the prover knows 2 values, x and y, such that x plus y equals some other value z, where z is public. And the way we would do that is basically that we just take this protocol again, and we say, let's say grab these guys. We're going to take that again, and we're going to, instead of committing, we want to prove x plus y equals z. We're going to say like let r equal that and let s equal g to the s, where public is going to be g to the x and g to the y, and g to the x plus y. So those are all going to be known, and we claim, the prover is going to claim that z is the addition. And we can do this relatively trivially. We can just say, well, if these values are public, these are secure under discrete log. So I can actually just amend this by, we don't need the whole protocol here. I think that we actually use the protocol a bit for the multiplication protocol. Moving past that, we can just say, have the prover publish z, and we can have the verifier say g to the x times g to the y is equal to question mark what claimed g to the z is. And if that is true, then we have this protocol for addition without revealing information about x or y. Because publishing z would reveal the additive sum of x and y, and if we had any more information about x and y, then we could probably sort of do some linear algebra on them. But just in the presence of z, there's not a whole lot left. So we can do that. So we get z, okay, we get addition. And the question is, can we get multiplication? And if you would like to see exactly how multiplication is achieved, I would encourage you to look at, and I'll put this in the notes, chapter, I believe, 11 or 12 of Proofs, Arguments, and Zero Knowledge gives a protocol for ZK multiplication. But with that in hand, we have a way to say, take the inputs to some addition or multiplication gate with maybe some inputs x and y, or inputs x and y, and say some output z. We have a protocol for proving that we know the inputs, and we can combine this in an arbitrary circuit. And ideally, what we would like to be able to do is we would like to do this without revealing z at all. And so that is what we actually do in practice. The next question is, if we get these things, what have we won? Well, with addition and multiplication, we've actually won. We've won or and, because we can compute, if we have some bits b1 and b0, we can compute the or of these bits, and this should all look fairly familiar here. But the direct addition of those two bits is not directly the same as or and, but we can say that the addition of the bits minus the multiplication of the bits is equal to the or value, and if we just multiply the two bits together, we get it precisely in AND gate. So with addition and multiplication inside of a ZK circuit, we can prove that we have computed some operation without revealing the actual inputs to that operation. So what we win actually is Turing completeness inside a zero-knowledge proof. So this says that if we have any program that we can express in Boolean gates, we can transform it to an arithmetic circuit and then run the protocol previously described, where for each gate we do this ZK addition or ZK multiplication step. And we can do that recursively all the way up to the output of whatever circuit is. So this is the sort of core intuition for why we like circuits with cryptography, is that we have a one-to-one correspondence between the circuits that we might like to compute and the Boolean logic that we might like to compute. So a lot of the time when we're hearing about ZK circuits or lookup tables, we're actually just sort of reinventing Boolean logic and the sort of foundations of computer science in the cryptography context, whether it's like lookup tables or indexing into arrays or whatever. So the like for instance, if you've heard of Plonk or Plookup, it's not that Plookup is trivial, but anyone who is looking at sort of like the history of how we compose these sort of gate operations could have quickly come to the conclusion that we're going to need some fairly basic operations like indexing into arrays and lookup tables for expensive computation. So the sort of next step into that is, well, so we're just sort of transforming traditional computing into this ZK language for circuits. And sort of like the hard question to answer after we have this sort of language for circuits is what's the most efficient way to express these circuits? Because the sort of way that I've alluded to up above is like one way that we might express these sort of circuits. But then if we have entire rows of circuits, there might be something more efficient than computing and proving each gate one by one. And there are actually several answers to this. But the sort of best answer that I am aware of, or the best two answers that I'm aware of, involve either something called the GKR protocol, which sort of creates a commitment to all of the gates in a row at the same time, and then runs this interactive GKR protocol to just prove that the entire row is valid. And then there's also an approach using fast Fourier transforms. These correspond to the techniques generally used in Snarks and Starks, respectively, is how we arithmetize and prove each layer of our circuit. And those different arithmetization schemes make different sorts of expressions more convenient or less convenient. For instance, it turns out to be fairly convenient to express a lot of different sort of more flexible arithmetization, or a lot more flexible sort of programming concepts using the arithmetization scheme used in Fry. So I think those teams working on transpilers from Starks into this sort of language are moving a bit faster than the Snark-based teams. So the final answer that we were trying to work up to today was, can we prove knowledge of the xi's, these guys over here, if the circuit is public knowledge and we claim to have some xi's that equal to y, well, that just reduces to a repeated running of each gate and sort of a sneak peek to sort of like the broader world is that we'd probably like to be able to do all of this more efficiently. And that's kind of what we achieve with zero knowledge circuits. So I think that's about all I had prepared for you today. I haven't published the site notes yet, so I'll get around to that in a couple of minutes. So before we close out, were there any questions about today's lecture?
I just have a clarification on what you said about the Starks versus Snarks DSLs. Can you clarify what you meant by why they were able to move faster?
Yeah. So as far as I understand, Starks are sort of easier to build certain opcodes for, and I'm not super deep into this, but as far as I've read through the Starkware papers, and the stuff put out by Polygon Biden, which is a Stark-based VM. Apparently there is a sort of structure in Starks that allows them to make an easier compiler from the Stark arithmetization, or targeting the Stark arithmetization from high-level programming language concepts like ORs and loops. I couldn't really give you better than that, since I'm not a ZK compiler engineer myself.
Yeah, no worries. I was just curious. It sounded really cool.
Yeah, it sounds interesting to me too, and I haven't really gotten a better answer than that.
No worries.
Yeah. Any other questions? All right. So next week is going to be our last week. And I suppose the intention there was, ooh, I got frogs. I got tears and frogs and claps. This is great. So next